Now the only thing in the topic that's left is your that's known as Faraday constant. So we're going to talk about, and then we're going to do past paper questions. So we're going to talk about Faraday constant. Then what's the Faraday constant? That's so Faraday constant is equal to, it's known as F. It's equal to 96,500 coulombs. And I'm going to explain where that came from. So it's a quantity of charge. Yeah, that's what your Faraday constant is. So what's where do you derive that? The formula for Faraday constant is F is equal to LE, where E is the charge on one electron. That's 1.6 times 10 power minus 19 coulombs. Your L is the Avogadro's constant, which is 6.02 times 10 to the power 23. That's your L, and obviously F has a value of 96,500 coulombs. In simple words, in very simple words, what that means is it's the charge on 1 mole of electrons. I mean, so it's simply a charge on 1 mole of electrons. That's it. Like, you know, the charge on 1 electron. So the charge on 1 electron is 1.6 times 10 power 23.
Mister, is this a new
Sorry,
topic?
it's Faraday constant. It's the same one. Minus 19 coulombs. Sorry. It's the same topic. It's just explaining what Faraday constant is. I said, so Faraday constant is the charge on 1 mole of electrons. So you've got one electron having a charge of 1.6 times 10 to the power minus 19 coulombs. So if you have 1 mole of electrons, how many electrons is that? That's 6.02 times 10 to the power 23 electrons, right? So how much charge would they have? That's going to be X. And if you find out X is basically 6.02 times 10 to the power 23 multiplied by 1.6 times 10 power minus 19 coulombs. And that basically gives you 96,500 coulombs. So there's no rocket science. This is simply Faraday constant over here is the charge on 1 mole of electrons. That's it. Okay, that is what Faraday constant is. And I mean, this thing over here is just F is equal to LE. That's Avogadro constant. That's the number of electrons that you have in 1 mole multiplied by the charge on 1 electron. So a single electron has this charge. So if you've got 1 mole of electrons, then it's 6.02 times 10 power 23. That's the number of electrons that you have. Is this clear?
Yes. So what is this F?
Yes, sir.
96. What is this F 96,500?
That's the charge on 1 mole of electrons. But try kar lo, calculate kar lo. It's you know that 1 electron has a charge of this, right? So if you have 1 mole of electrons, that means you have these many electrons. So you multiply the two, you get this. Is that clear?
Yes, sir.
I said the point is, where do you use this? Okay, so just remember, Faraday constant is simply the charge on 1 mole of electrons. That's it. So that's just remember that 1 mole of electrons has this charge. You would need another formula, which is Q is equal to IT, which you already studied in physics. That's the I would be, the T would be in seconds, and the I is the current in amperes. You already know this formula. That's if you know, if there's a wire, there's current, and there's current flowing for a particular time, you can figure out the charge that's flowing through the circuit. So you would need that formula as well. As anyway, so where do you use this? The way you're going to use this is, you're going to use this in a moles question. A lot of times, I mean, they would be simple moles questions, not that difficult. For example, you might be asked, calculate the volume of H2 gas produced. So calculate the volume of H2 gas that's being produced if 2 ampere current flows for 30 minutes uh, through H2SO4 to electrolyze H2SO4. So first thing, let's quickly do the electrolysis of H2SO4, which is kind of pretty obvious. It's and remember it's inert electrode, so you've got these two electrodes, and there's electrolysis that's happening. Remember, the electrolysis is happening for 30 minutes. H2SO4 has two things. It's got H plus one ions. Now remember, there is H plus one ions because there is H2SO4, and there's SO4 minus two ions, right? So you've got your negative cathode, you've got your positive anode. Electrons are going to be gained over here. What else do you have? You've got water as well. So water gaining electrons, water losing electrons. You can remember, water, don't write it as H plus 1 or OH ion. So who's going to gain electrons? Is it going to be H plus 1? Is it going to be H2O? And who gains electrons? The one that has a higher E naught, right? So open the data booklet. So we've got two candidates, H plus 1 and H2O. So open the data booklet. I did have the data booklet. Just this one is the data booklet. Let me rub this off. So remember, I have H plus 1 trying to gain electrons, and I've got H2O trying to gain electrons. So find out H plus 1. So there's H plus 1 gaining electrons, that's zero potential, right? And find out water gaining electrons. So right next to it, there's water gaining electrons, and that's 0.83 volts. So who's going to gain electrons? The one that's having a higher potential, which is the first one, which is H plus 1 ions. They're the ones that are going to gain electrons. So that's your equation, 2H plus 1. And they're going to gain 2 electrons, and they're going to form H2 gas. Is this clear?
Yes, sir.
So it's going to be your
Yes.
so it's going to be your H plus 1 ions that are going to gain electrons, right? And I'm not going to do the further. We can actually do the rest of it as well. On this side, who's going to lose electrons? It's the one that has the lower E naught is the one. The one that has the lower E naught is the one that's going to lose electrons, right? So it's either SO4 minus 2 or H2O. So go back to the data booklet. Now lose electrons, that's backward. So you've got two equations for water that is losing electrons, SO4 minus 2, that's losing electrons. So who likes to lose electrons? The one that has the lowest potential, which I think is 1.23 volts. The other one is 1.77 volts. This one is 2.01 volts. So it's going to be water that would lose electrons to form oxygen and 4H plus 1. So write the equation in the backward direction. As anyways, that had nothing to do with the question. Coming back to the question, how would you apply the Faraday constant to this? So first thing, the only information that's given is that the electrolysis is happening for 30 minutes and there's a current that's flowing for a 2 ampere current. So I can figure out the charge, which is, I can use Q is equal to IT, and I can figure out the charge that's flowing through the circuit. So it's 30 minutes. Turn that into seconds. So 1 minute has, I think, 60 seconds. So it's 30 into 60, that's the time, and the current is 2 amperes. So can anyone do this and tell me what the value is? Or we can have the... It's 1 second.
3,600.
8,600?
3,600.
3,600. So you got 3,600 coulombs, right? So you got 3,600 coulombs. Now the other thing is, what do you do with that? You know that 3,600 coulomb charge is flowing through the circuit. Now, what's flowing through the circuit? It's electrons that are flowing through the circuit. I know that 1 mole of electrons has how much? That's the Faraday constant. 1 mole of electrons has a charge of 96, 500 coulombs, right? Now, based on this charge over here, I can figure out the moles of electrons. So, how many moles of electrons are flowing through the circuit if I have 3,600 coulombs? So, I can use ratios and I can figure out the moles of electrons. Can you do that? It's going to be 3,600 divided by 96,500, right? So 3,600 divided by 96,500, and that gives me 0.0373 moles, right? Is that correct?
Yes, sir.
So the purpose of the Faraday constant is that it's a relationship between charge and moles of electrons. Like if you know the moles of electrons, you can figure out charge. If you know the charge, you can figure out the moles of electrons. This ratio comes in very handy. Like if you know what what the charge on 1 mole of electrons is, you can figure out the moles of electrons. If you know what the charge that's flowing through the circuit, you can just convert that into the moles of electrons. Is that clear to everyone?
Yes, sir.
Yes.
So
Yes.
it's, I think it was 373, right? 1 second. Yep, 0.0373. So I've figured out the moles of electrons. Now I already had an equation. And now I know the moles of electrons. How many moles I have? There are 0.0373 moles of electrons that are flowing through the circuit. So the equation says that 2 moles of electrons, they produce 1 mole of H2. So according to the ratio, 0.0373 moles of electrons are going to produce how many moles of H2? They're going to produce half of that. So it's going to be 0.0373. And it's going to be divided by 2, and that gives me 0.01865. Is this
Sir,
clear?
multiply by अपने उल्टा लिखा था
क्या?
2 electrons per 1 mole of hydrogen ना
Yeah.
so 0.0373 moles per x electrons
हाँ.
तो आपने 2 multiply करना
Divide करना.
0.06
Divide करना ना, क्या कह रहे हो? 2:1. 0.0373 ratio
नहीं,
x.
so that is what I'm saying here 0.0373 दूसरी side right side को लिख 0.0373 राइट साइड पे लिखना है क्योंकि मोल्स तो हमारे पास हाइड्रोजन के 1 मोल है ना मोल्स के नीचे वी राइटिंग द मोल्स अंडर द मोल ना यू राइटिंग इलेक्ट्रॉन्स के नीचे मोल्स
हाँ, तो this is moles of electrons, ना?
this is 2 electrons number of electrons
This, I didn't get what you're saying. It's the equation says that 2 electrons produce 1 H2, right?
right can I use the marker
But then I'm not.
I mean this is number of electrons
हाँ.
and this is the number of moles right
नहीं, this is नहीं. Let me clear this. And let me. So let me clear this. 1 second. So the point is, this is not number of electrons. It's basically, this is the ratio. 2 electrons produce 1 H2. 2 moles of electrons are going to produce 1 mole of H2. 2,000 electrons are going to produce 1,000 H2. Ibrahim, do you get the point? ठीक है, moles
of electrons producing 1 mole of hydrogen
2 moles of electrons produce 1 mole of H2, right?
Right.
ठीक है, mole is just a, I mean 2 dozen electrons are going to produce 1 dozen H2. ठीक है, moles is just a unit. ठीक है, this is the ratio. Like two of these would produce one of this. ठीक है. So So 0.0373 is going to produce 0.01865. Is that clear? And the
Yes.
last thing is you were being asked to figure out the volume. So it's multiplied by 24 dm cube. Make sure it's at RTP. And if you do that, so it would become equal to 0.4476 dm cube. Or is this clear?
Yes, sir.
Yes.
So most of your Faraday constant questions are going to be exactly this way. That remember, the Faraday constant is simply the charge on 1 mole of electrons. And this, I mean, you can figure out the charge that's flowing through the circuit by simply Q is equal to IT. Like if you know the current, you know the time it's flowing for, you can measure the charge in coulombs. And once you do that, once you have the charge, the simple thing is that you can just use ratios, right? It's 1 mole of electrons. You can convert charge. Otherwise, you can convert charge to moles of electrons or moles of electrons into charge. So the question could be phrased in many different ways. Uh, Sometimes they might give you the volume, and you might be asked to figure out the time it requires for the electrolysis to happen. Like if you want to collect 0.448 dm cube of, let's say, gas, and the question is asking you to find out the time it's going to require if there's a current of 2 amperes, right? So what you're going to do is you're going to find the moles of H2, you're going to find the moles of electrons. Once you have the moles of electrons, you can figure out the charge by using this ratio. Once you have the charge, you can just put Q is equal to IT and you can figure out time. So the question could be phrased in both ways. So that's about it. That just a brief idea. It's most of the questions are going to be very simple. Just remember Q is equal to IT, and just remember that the charge on 1 mole of electrons is 96,500 coulombs. So you can convert charge to moles, you can convert moles to charge, whatever is required. Is this clear?
Yes, sir.
Yes.
Achha, so we're going to start with, I think we're done with, somebody was talking about Lenz's law. Just one second. Not data booklet. Just one second, let me open the syllabus one, the latest one at least. TK, that's not for the ones who are appearing in October, November. TK, in 2022, the syllabus is different. Not that different, actually. So, that's this one, I think, yeah. F is equal to IT, Q is equal to IT, we did that. Standard electrode potentials, we did the Nernst equation, we did most of it. We did this Nernst equation, yes. So this one is new.
Did you do that? I mean, the Nernst equation. ये कब किया?
I'll explain the Nernst equation. I'll explain this, but this one is new. This has been recently added, gives free energy. So we're going to talk about that. It's simple actually. It's just moles multiplied by the E naught cell into Faraday constant. I'll explain that later. Nernst equation. I'll just quickly go over that one more time. 1 second. So we did the Nernst equation probably on Monday. Just 1 second. And we did the homogeneous catalyst example as well. This was the Nernst equation. I told you that. So what I told you that that most of these electrode reactions, like if you have an electrode, these electrode reactions are equilibrium reactions, which means they're equilibrium that are attained at under standard conditions, which means that the temperature should be 25 degrees centigrade and the pressure should be 1 atmosphere and the concentration should be 1 mole per dm cube. But if you alter the equilibrium, the potential would also change. Like if you increase the concentration of Cl ions, the equilibrium is going to be altered. It's going to shift in the backward direction. And when it shifts in the backward direction, a lot more electrons are going to be produced, and the electrode would be full of electrons, and the electrode would be more negative because of these electrons. So the potential would drop. It's not going to be as positive as compared to standard conditions. Ibrahim, is this clear?
No, yeah, sorry, sir, I wasn't listening.
Yeah, I'm just saying that this is an equilibrium reaction, right? You know what Le-Chatelier principle is. You know that
Thank you.
if you increase temperature, endothermic is favored, decrease temperature, exothermic, you change pressure, etc. So if you increase the concentration of Cl ions, where would the equilibrium shift? It's going to shift in the backward direction,
To the
right?
left. Yeah.
So it's going to produce more electrons now, right? So imagine
Okay.
there being more electrons on your electrode.
Oh,
So that means the potential would drop. It's going to decrease. It's going to become more negative. Is that clear?
I see. Yeah.
So I told you that if equilibrium shifts to the left, the potential decreases because more electrons are going to be produced. Vice versa, by any of your changes, like if you do any changes, if you change pressure, temperature, or concentration, and the equilibrium shifts forward, then the electrode is going to have fewer electrons because all the electrons would be consumed by sodium ions. So the electrode whose voltage you're trying to measure would have fewer electrons, and it's going to become more positive. So equilibrium shifts to the right, the potential increases. It's going to become more positive.
So yes, because electrons are used up, right?
Yeah.
Take care, right?
And in this case, it's going to become more negative. Like we had the electrode diagrams, TK. 1 second. Somewhere. That's this. I said we had all these electrode diagrams. So just imagine that if I have Cl2 in equilibrium with 2Cl minus 1, right? So if I have more Cl ions, what would more Cl ions do? They would start to lose electrons, right? So there would be more electrons on this platinum electrode. Is this clear?
Yes, sir.
So there's going to be more electrons on this platinum electrode, and so the potential would become more and more negative. It's not going to be as positive as which it was previously. So just remember this idea that you just use your Le-Chatelier principle. Equilibrium moves forward, that means it's going to become more positive. So these potentials are not fixed. They're only fixed under standard conditions. If you change the conditions, the potential would very slightly increase or very slightly decrease. Not by a huge margin, but just slightly increase or slightly decrease. So that was what happens, that under non-standard conditions, the potential increases or decreases for an electrode. So all the potentials that are given over here, so where was this one? So all the potentials that are discussed or given over here, they're all under standard conditions. So if I, for example, if I just focus on this lead electrode, like if I increase Pb4 plus concentration, what's going to happen to the potential? Can anyone tell? If I increase Pb4 plus concentration,
Shift
It
to
will
the
shift to
right.
the left. Yes,
um,
to the
it
right.
shift to the right, and if it shifts to the right, the potential would increase. It's going to become, instead of being 1.69, it's going to become probably 1.8. Is that clear?
Yes, sir.
And vice versa, if it shifts to the left, like if I increase Pb2 plus concentration and it shifts to the left, it's going to become more negative. It's going to decrease. It's going to be 1.5 or something, but not by a huge margin, just by 0.1 volts or 0.2 volts, something like that. So now, what's the Nernst equation? The Nernst equation is that we just figured out that it's going to become higher or lower. The Nernst equation is the formula that's going to exactly give us what that potential is. It's going to exactly tell us what that potential is. So, so it's this equation. It's the standard potential of the electrode plus 0.059, which is a constant. Z is the number of electrons, and the log of oxidized species over reduced species, the concentration of the two species. Which one is the oxidized species? It's the left hand side. I mean, whatever, like in your data booklet, whatever is on the left hand side, that's your oxidized species, its concentration. Which one is the reduced species? It's the one that's in the equation in the data booklet, the one that's on the right hand side. So for example, I have this
Sir, what
reaction.
is Z and how do we know?
Z is the number of
uh,
electrons,
So how do we know कि कितने electrons हैं?
but it's given in the equation. For example, this is the electrode, right? Copper 2 plus, copper 1 plus, right? In equilibrium, and the E naught is 0.15 volts. I mean, this is exactly this copper equation, can't you? It's exactly this one. It's where is this one? Copper 2 plus 1 electron to form copper plus 1 in equilibrium, and that's plus 0.15, right? So I've taken that equation and I've changed the concentrations now. The concentration of copper 2 plus is 0.15 mole per dm cube, and the concentration of copper 1 plus is 1.5 mole per dm cube. So obviously, the potential is no longer going to be standard potential. It's not going to be 0.15 volts. Is that clear?
Yes, sir.
Yes.
And because the copper 1 plus has a higher potential, sorry, a higher concentration, the equilibrium is more likely to shift to the backward side, right? And if it shifts to the backward, it's going to decrease. More electrons are going to be produced. It's going to become more negative. So it's probably going to come out to be less than 0.15. Is that clear?
Yes, sir.
So we're going to use the Nernst equation to tell us exactly what that potential is. So it's going to be the standard potential E naught, that's E naught, 0.059 divided by Z, which is the number of electrons. The number of electrons in the equation over here is 1. So it's 0.059 divided by 1. And log of oxide species, remember I told you the oxide species is the one that's on the left hand side. This one, 0.15.
सर ये 0.059 क्या है?
That's a constant. That's just a constant.
ठीक है.
ठीक है, Adam? So it's always a constant and divided by the log of reduced species. Reduced species is the one that's on the right hand side. You do that, you calculate this, take log that's on your calculator. It's going to give you exactly what the value is. That's the new potential. You can do this for anyone. It's just remember the equation. For example, this one. For solids, remember the concentration is always taken as 1. So, I mean, for solids, the concentration is even in equilibria, in Kc and Kp, it's always taken as 1. So this reaction, I've really decreased the silver ion concentration. Instead of the standard conditions, I've taken it as 0.0001 mole per dm cube. That's very, very low. So that indicates that the equilibrium is going to shift in the backward direction. And it's going to become more, not positive, more negative actually. I don't know why I write positive. If it shifts to the backward side, it's going to decrease. More electrons are going to be produced, so it's going to be decreasing. So I'm going to use the Nernst equation, which is the new potential is E naught, which is 0.8 volts, the one that's given in the data booklet, plus 0.059, which is the constant, divided by Z, number of electrons, that's 1. Log of oxide species, the one that's on the left side. Actually, it's this one, sorry. What is this one then? Let me forget this. This one. 0.8, 0.059 divided by 1, which is the number of electrons, log of oxide species, the one that's on the left hand side, divided by the log of reduced species, the one that's on the right hand side. Solids would be taken as 1. You solve this, it comes out to be 0.564. Is that clear?
Yes, sir.
So just remember the Nernst equation. That's it. Always remember the Nernst equation that this is the concentration of the left hand side thing. This is the concentration of the right hand side, the thing that's appearing on the right hand side. Z is the number of electrons. E naught is the old potential, and E would give you the new potential. Is that clear? So now what we are going to do is we're going to do past papers of this. So this one, electrochemistry. Uh, I'll send the worksheet as well. Starting with the first one is actually the most difficult one actually. So for the first one is kind of the most difficult one, the trickiest one. So he's saying that there's this overall reaction for photosynthesis, and that's shown. So you've got carbon dioxide and water molecules, and so this is a photosynthesis reaction. You already know this, and it's given you the half equation that like water is oxidized in this process. So this is the oxidation reaction, right? He's saying use these equations to deduce the half equation for the reduction equation. So we want to figure out like who's gaining electrons. Okay, we want to figure out the reduction equation. Now we haven't done anything like this because what we were doing was in all our questions, in all the questions that we have studied, we had two equations. Not this. Just one second. I said, so every time we had, I mean, this is electrolysis. Just one second. I said, every time we had, let's do a simple one. Every time we had two equations, right? This one is also a chain reaction. I said, we figured out a reduction equation. Whenever we were trying to figure out a reaction, we had a reduction equation and we had an oxidation equation, and that gave us our overall reaction. Like you added up the reactants, you added up the products, and you made the overall equation. Every time we did this, even in the simple cells, like we did earlier, we had two half equations, one gaining electrons, the other one losing electrons. We made the number of electrons gained and lost equal, and we came up with the overall equation. Is this clear?
Yes.
Now the problem over here
Yes.
is, so now the problem over here is the question is very simple. It's not that difficult. It's the same thing. It's you have a reduction equation, you have an oxidation equation. You combine the two equations up, and you get the overall equation. We have been doing this in pretty much all the reactions that we did. Who gained electron, who lost electrons? You added them together, and you ended up getting this overall equation. Now the question is, the reason the question is trickier is that they've given us the overall equation. They gave us the oxidation equation, but this equation is missing. So, like, if this equation is missing, how do you figure out this equation then? I mean, that's the question. That's why it's tricky. That you have the overall equation, you know that this equation and this equation got added up to form this equation. So how would you do the reverse now? Okay, that's the tricky part in this question. So we're going to try and figure out how to do this. For example, we know the overall equation, right? So he has already stated that the water molecules are losing electrons, right? To form O2 plus 4H plus 1 plus 4 electrons, right? So the water molecules are losing electrons. Why are they losing electrons? Because the oxidation state of oxygen is changing. Like if you look at oxygen is -2 over here, right? And what is the charge in O2 over here? It's 0, right? And why are they losing 4 electrons? I mean, that's the only thing that's the oxidation state of oxygen is changing. It goes from -2. H is +1. H is still +1. So it's not because of H that they're losing electrons. It's because of oxygen that they're losing electrons. Oxygen goes from -2 to +2. So that means it lost electrons, right? And there are two oxygens over here, the two oxygens over here as well. So that's a total of 4 electrons. Is this clear?
Yes.
Yes, sir.
So that's your oxidation part. Now coming to the reduction part. So how many oxygen molecules? So the question is, let's focus on this, the first equation. Okay, let me write this. Hopefully we do have enough time for this. So we've got 6 CO2 molecules. And I'm going to add C6 plus 6O2. So now one thing I can actually do now is I can sort of figure out that I can kind of figure out that this is my oxidation equation. So where do CO2 and H6, C6, H12O6 come from? They probably come from a reduction equation, right? So I'm going to write my reduction equation. Then I know that 6 CO2 molecules are turning into, because the two equations are going to add up. I mean, these two equations are going to add up. And they're going to add up to give me this glucose equation. Okay, is this clear?
Yes,
Right?
sir.
I mean, how did you figure out the fact that this is your reduction reaction?
Which one?
I mean, this carbon dioxide turning into
This one.
glucose.
Just 1 second. The way I figured out was, this is one of my half equations, this is my other half equation, right? Now, I knew one of my half equation. So I kind of knew that the water and the O2 are basically coming, because these two equations, they add up to give you this, right? Is that clear?
Which two? अच्छा जी हाँ ठीक है.
Balki, let me write it, ऊपर नीचे हो गया, let me just write it in the proper way so that it's clearer. ठीक है, just hold on 1 second. ठीक है, forget this reduction equation. As anyways, so you have an oxidation equation, you have a reduction half equation. The two are going to combine together. Okay, so these two are going to combine together, they would add up, and they would give me this final overall equation. So it should give me 6 CO2 plus 6 H2Os, right? And it should give me C6H12O6 as well, plus 6 O2 molecules, right? So I kind of know that the oxidants are coming from which equation? The oxidation equation, right? And the water molecules are coming from which equation? They're also coming from the oxidation equation. So where is CO2 and the glucose coming from? They must be coming from the reduction equation, because they must be coming from the glucose. I mean, these two would be coming from the reduction equation because they are missing in the oxidation equation. Is that clear?
Yes, sir.
Okay, Ibrahim, is this clear?
Yes.
Yeah.
So we're trying to figure out this missing equation. The two equations add up to give me this. Now the tricky part is that how many oxidants are produced, right? How many oxidants are produced over here? The oxidants produced are, in the final equation, there's 6 O2 molecules, right? So what I need to multiply this by is 6, right? Because, I mean, the two equations should add up to give me 6 O2s, right? So I need to multiply this by 6. So that would give me 12 over here. It's going to give me 6 O2s. It's going to give me, what's 6 into 4? That's going to give me 24 H plus 1 ions. And this would be 24 electrons. Is this clear?
Yes.
So the only way I can get 6 O2 molecules over here is that the oxidation equation had 6 O2 molecules. Then this equation would add up with this equation to give me 6 O2 molecules. So that means I have to add everything by 6. Clear? Okay, is this clear to everyone?
Yes, sir.
Acha, what's missing over here now? Let's focus on the other equation. In the product, there's 6 CO2. Where are the CO2s coming from? So that means there should be 6 CO2s, right? So that these two add up to give me 6 CO2s. And how many electrons are being lost over here? That's 24 electrons, right? So remember, the number of electrons gained and lost, they must be equal. So that means CO2s must be gaining 24 electrons. Is this clear?
Sir, but
Yes,
there's
sir.
one question. Okay, in the above equation, you multiplied 6 with the entire equation.
Yeah.
What with this carbon dioxide or turning glucose with this, you only multiplied carbon dioxide over
Nee, because
like,
that's because I was only focusing on that there were 6 CO2s missing, right? So that they must be coming from the reduction equation, and there was only one glucose. I mean, it's already balanced: 6 CO2s, 6 carbons, and there's 6 carbons over here. Is that clear? Achha, plus, it's not just the electrons that are lost and the electrons gained. There's 24H plus 1 also getting produced over here. And you can't see any 24H plus 1 over here. So that means if 24H plus 1 are being produced in the first reaction, then there must be 24H plus 1 that would be gained in the second reaction. That's the only way they would get cancelled out, right? Do you get my point? Because in my final equation there is no H plus 1. So that means all the H plus 1 got used up. So if the first reaction there are 24 H plus 1 getting produced, so in the second reaction 24 H plus 1 must be getting used up. And also another thing, and that is that on the left side you've got how many water molecules? You've got 12 water molecules. Whereas over here in the final equation you just have 6 water molecules. That means out of these 12 water molecules, 6 of the water molecules must have gotten used up. Only then would everything balance out to give me this. This is my final equation. The two equations must add up to, so I'm just going to repeat everything, okay, just for clarity. The first thing was I had just my oxidation equation. This equation was completely missing. So I just had my oxidation equation. And I knew that it was losing 4 electrons. But in my final equation, the overall equation, I had 6 O2s. So I multiplied everything by 6 so that when I add this equation with this equation, I get this equation. So I multiplied everything by 6. And that led me, that gave me 24 electrons being produced. So if there were 24 electrons being produced, then in the reduction equation, 24 electrons must be getting consumed. If there are 24 H plus 1 getting produced in the first equation, in this reduction equation, there must be 24 H plus 1 that must be gained. And I figured out that the 6 CO2s and the glucose is coming from the reduction equation. So it's just like solving a math equation. There's this missing variable, but this missing variable is this entire equation. And over here, I have 12 water molecules. Now, I need to, if I add them up, I'm going to get 12 water molecules on the left side. So I need to cancel some of the water molecules as well. So if there are 12 water molecules over here, then in the second equation, there must be 6 water molecules on the other side, so that when you get 12 water molecules over here and 6 water molecules on the other side, the water molecules also cancel out and you get this equation. So that's your reduction equation. Is this clear?
Yes.
Is this clear to everyone?
Not really.
Yeah.
So let's talk about this tomorrow then. We'll discuss this one more time tomorrow with more examples. I'll actually do more examples like this. Then we'll talk about this in detail. We don't have enough time, so we'll discuss. We'll do more examples like this. Okay, then take care.
Very sad.
Thank you.
Okay, thank you.
That is
Thank you.